So as I was saying, this is a system we are considering as far as we determine the pH of that system, and I forget what the pH ended up being. Got the wrong sheet of paper in my hand. Ended up being 3.60. And that was with a ratio of 0.18 molar to 0.13 molar. You guys recall this? Okay, now, if I remember correctly, I set number 6 up in such a way that, yes, it was 0.18 molar and 0.13 molar, but the way I'd originally set it up was 0.18 moles and 0.13 moles, and I told you it was in 1 liter of solution. You guys, you can look at your papers and see that, right? I did that intentionally, okay? 1, it made our lives easy here, where we could just go ahead and calculate pH from the molarities. And 2, now when I say, hey, we're going to add 0.015 moles of sodium hydroxide to this mixture, we can also see how that's going to influence this material up here. So, yes, we're going to look at the stoichiometry piece first, but we're not going to do it in the, when I say stoichiometry, you guys are thinking of doing this long calculation, right? We're going to do it in such a way that it looks like an ice table. It's not really an ice table, but it's going to look like an ice table. So can I go ahead and get rid of the molarities here and put mole? You guys okay with that?
Yeah.
Since I'm giving you guys moles in 1 liter solution, we can do this. Now, we are going to add 0.015, I believe, isn't it?
Yes.
Moles of sodium hydroxide to this mixture. What can the sodium hydroxide react with? Just bringing you back from Florida. What can the sodium hydroxide in this mixture react with?
Could it be the C?
The acid or the base?
The acid.
It's going to react with the acid. Would you agree? And it's going to react with it being a strong base in a 1-to-1 relationship. You guys comfortable with that? Okay? I'll write it out just for fun. You don't have to write this down. Oops. What are my products? Sodium. Cu. Plus water. That's the methanoate ion, by the way, just in case you wanted to know. Plus water, okay? So sodium methanoate. Anyway, moving on. And water. It's a 1-to-1 relationship all the way through. So if I'm adding the sodium hydroxide, what's going to happen to the concentration or the amount of this, the moles of this? It's going to decrease by how much? 0.015 moles. So from here, we're going to add, it's going to take away 0.015 moles. What's going to happen to the concentration of this? The methanoate ion. Well, remember, the hydroxide is taking away the hydrogen, reducing the amount of this, leaving more of that. Would you guys agree? So this is going to increase by 0.015 moles. Would you agree? We're producing more of this. We're reducing the amount of this. Okay? So, after addition of base, what is our new number of moles of the acid going to be? isn't it like 0.165 or something like
Yeah,
that?
0.165.
And this is going to be 0.145. Is everyone hunky-dory about what happened? Now, let's think this through. We just added a base, a strong base to a solution. What do you think should happen to the pH?
Move towards neutral.
This is not a hard question. It should increase. Would you agree?
Yes.
By adding a base to a solution, we should increase the pH. Before we do any other calculations, let's think this through. What happened to the amount of acid? Decrease. What happened to the amount of base? Increase. Already we're thinking to ourselves, hey, that's probably going to increase the pH, right? Let's find out by how much it's going to increase the pH. Now, we can think of it two ways. One, I've already shown you that we can just look at the ratio of the moles instead of the ratios of the molarities because of the fact that the concentration or the volume stays the same, right? However, since we're in 1 liter of solution, we can think of them as molarities also. It doesn't really matter. But would you guys agree that the Henderson-Hasselbalch would probably be a good thing to use here again? We know the moles or the molarities of this. So let's just go ahead and plug it into Henderson-Hasselbalch. Some of you guys have probably already done this. Okay, and in this case, it's going to be 0.145 over 0.165. Okay. Go ahead and throw that in there, see what you guys get. What'd you get?
0.13. Yeah. 3.69.
Anyone agree? Yeah. Okay. Did the pH increase? Absolutely. We anticipated it increasing. Here's an interesting question though. We just said that a buffer system would try to maintain a pH as closely as possible. It went up by 0.09 of a pH unit. Okay, is that significant or not? Well, let me ask you this question. What did we add to this? Sodium hydroxide, a strong base. If I had added this number of moles of sodium hydroxide to just 1 liter of pure water, what would the concentration of the sodium hydroxide have been? 0.015 molar. Would you guys agree? Watch this. So now we want to find the pH of a sodium hydroxide solution. Let's just do that for fun. How would you find the pH of a 0.015 molar sodium hydroxide solution? Take the negative log of the 0.015, which would give us the POH, and we subtract that from 14. I think most of you are already figuring this out. I don't know, 2.4-ish? Can't remember if I went the right way or not. Maybe it's 2.6. Oh wait, I went the wrong way. Yeah, 1.82, is that what you guys got?
Yes.
Okay, now that's the POH, so therefore pH is going to be 13.18. Now watch what happens. What's that? 12, my bad. 12.18. So, if I just add 0.015 mole of sodium hydroxide to 1 liter of water, pure water, that's what the pH would be, 12. If I add 0.015 moles of sodium hydroxide, strong acid, to the buffer system that we had already created, what happened to the pH? We're at 0.09 pH units. Did it resist changes in the pH? Yeah, by quite a bit. And that's the entire role of a buffer system, is to do that. Here's what I would like to do. I want you guys to try one of these on your own. What we're going to do, and I'm going to try to do this with minimal work on your part, so I'm not going to give you a completely new problem. What I want to do is take example number 5. I don't know if I'm going to be able to do it with example number 5. Okay, here's how we're going to do it for example number 5. Assume example number 5. Now listen, notice how this is why I left the pages that way. If you want to open it up this way, you don't have a lot of room to do things down here, I don't think. So if you want to do this over here, that's fine. But what I want to do is let's assume that we have 1 liter of solution in example number 5. Are you guys with me on this? So how many moles of HCN are there? 0.25. And how many moles of KCN? 0.17. Okay. Let's add, just for fun, stick with the 1.015. Let's add 0.015 moles of hydrochloric acid to that solution. Add 0.015 moles of hydrochloric acid to the solution in number 5. The buffer solution in number 5. You guys following what's going on there? Again, I'm trying to keep it as simple as I can, but also let you guys have the experience.
What was the pH in the original one?
I don't know.
9.14.
I don't know. I can't remember. Yes, 9.14. Now, obviously, I don't know the answer to this because I just made this problem up. was 9.14? It was 0.25. 7? 1.7?
7.
What's the hydrochloric going to react with? Cyanide ion, right? So what's going to happen to this? It's going to decrease by 0.1015, producing more of this. Are you guys following that idea? Okay, because the H so that's going to create some more HCN in the amount of 0.015 moles. So over here we're going to have 0.265 moles, and over here we're going to have 0.155 moles. You guys concur? Okay? And so now you just throw it in. Now, to what we had done before. So the pH is going to be equal to the pKa plus the log of 0.155 over 0.265. I don't know what you guys ended up getting. 9.08. Okay, so this time our pH changed by 0.06 of a pH unit. Okay, what would happen if I had put 0.015 molar hydrochloric in pure water? Well, we already know the answer to that. It was the 1.82 that we got from the previous question. Okay, so obviously you can see it does a nice job of resisting changes in pH. Okay, I'm sure on the assignments that I gave you guys out of the book, there's a couple of those on there. I try not to go too crazy on it. You know, do one, maybe do two. Again, they flat out said they're not going to have the omission statement. You will not be required to do this. I still feel comfortable with you guys having done it a couple of times. Next, we have some graphs to analyze. Now, I ended up see if that works. I don't think my cable's going to stretch all the way over, so we'll do the best we can here. All right. These diagrams I'm going to be showing you came out of the information that's in your textbook. Actually, these are the diagrams that are in your book. The graphs, as it turns out, are from the book that I'm hoping to purchase for next year, since your books are 10 years old, and the AP says that you have to have books that are at least newer than 10 years old. Now, whether I'm actually going to buy books or not, I don't know. But anyway, so these little graphs I stole from the book that I want to get, just in case. Anyway, moving on. So it matches up pretty well, although not exactly. We'll make it work for us. Put it this way, on almost every graph that we look at, yours go up 250, right? If you look on, you're only looking at one graph, if you flip through the rest of them, they only go up to 50 milliliters. These go up to 80 milliliters. What we're going to do is make our halfway point at 25 milliliters, which is, I think, clearly labeled on your graphs, right? Yes. So what you're are the shapes and some other considerations that I'll show you in a second. Anyway, the one thing I do like about what your current textbook uses is this particulate diagram, because this is showing up more and more often on the AP exam. The book that I'm looking at doesn't have as many of the particulate diagrams, so this is actually kind of good if we're looking at this. All right, our first graph that we're going to look at is the titration of a strong acid with a strong base. As you can read through the information there on the top page, I think it's 7 now, isn't it? 5. Oh, really? Is that it? Okay, top of page 5. This is a really terminology-driven kind of concept here when we analyze titration curves. Some of these terms you're already familiar with. Obviously, indicator. You guys are very familiar with indicators, yes? Sure. Nope, not yet. I was trying to remember if you were here yesterday. Anyway, indicator, you guys remember, are going to, an indicator is going to change color depending on whether it's in an acidic or basic solution. So it just tells us when we have reached the second term end point. Okay, so the end point is what happens when the indicator changes color. That means we're done, we're at the end of our titration. Theoretically, we want our endpoint to be where or within the range of the equivalence point. The equivalence point is the stoichiometric amount of material. When the amount of acid has completely neutralized the amount of base, okay, or vice versa, the base has neutralized the amount of acid, that would be called the equivalence point. Anything beyond the equivalence point is going to be either acidic or basic, depending on which way we're going. Now, if we go back to our, what did we do? Sodium hydroxide and acetic acid, right? Our equivalence point happened when the amount of sodium hydroxide exactly equaled the number of moles of acetic acid. We didn't know that, though, because at that point in time, the solution was, theoretically, neutral. Okay? When did we end the titration? When it went just a little bit over neutral. Remember, we were looking for that really faint pink? Okay? At which point that was the end point. As you can see here, well, this isn't a good example yet. Phenolphthalein changes color up starting at or around a pH of 8, just slightly basic. Okay? So obviously, when we did our titration, we were up into this region. However, we were not titrating a strong acid and a strong base. We'll cover that here in a second. Anyway, again, this is a strong acid, strong base. Initially, you can tell it's a strong acid because where does the pH start? Right around 1, okay, which would be like a 1 molar hydrochloric acid. Sorry about that. A 0.1 molar hydrochloric acid solution. Okay, so a couple of features you're looking for. If you see a really low starting pH, that means you're starting with a strong acid. If it were up in this range, you would be thinking it was a weak acid for the same concentration. Okay. Initially, as we add the sodium hydroxide, the pH doesn't change very much because we're only adding very small amounts of sodium hydroxide. It's only neutralizing very small amounts of base. Here's another term that we're going to see. I don't want to cover buffering region yet. It's the last term in that list, inflection. That's what we're going to call this really rapid change in pH. It's called the inflection region. I don't know if you guys have heard that term when you guys have looked at graphs before or not. You guys use that? Okay. So the inflection region here is when we get a really rapid change in the pH. Okay? And so what will happen is when you have a strong acid versus strong base titration, obviously at exactly the instant that you have the equivalent amount of acid and base in there, the products, if you remember, are a salt. For example, if I look at sodium hydroxide and hydrochloric, the results of this are a salt which when these things are floating around in water, neither one of them are going to contribute to the acidity or basicity, and water also not going to change the acidity or basicity. So we have a completely neutral solution. So right in the middle of that inflection in all these graphs that we're going to look at is what we call the equivalence point. And if you carry that over, you're going to run into what the pH of the solution is. So when you're looking at the inflection area, the middle of the inflection area is going to be the equivalence point, and that's going to give you the pH of that solution at that time. That's when the solution has been neutralized. Okay. What are some other things I want to look at here? The half equivalence point and the buffering region for a strong acid and strong base are really moot points right now. Doesn't mean much to us. You'll see where it does apply here in a little bit. What else do I want to do? Yeah, about the only other thing I want to point out is, as we continue adding base, obviously look what happens to the pH. It just levels off almost because it's all base now. Okay, next. Oh, shoot. What do you think, just out of curiosity, and I don't think I have one on here, I might. Yes, I do. What do you think the titration curve for a strong base to a strong acid would look like? Okay, so if you flip the page over, I think I have that labeled already, or at least I have a graph there, labeled strong base with strong acid, right? Okay, and we still have, I know there's a 25 here and a 0 here. We've got pH over here. What do you think the shape of that curve would look like? Inverse, okay. Where's it going to start? Towards the top, up here somewhere, wouldn't you imagine? Up getting close to the 14 area. So we'll call it here. What do you think the shape's going to look like? Maybe something like this, until it gets really close to that, and then what are we going to see? Yeah, that inflection. And where's it going to intersect the halfway mark? Right around the 7 area, so about right there. And then it's going to continue. You would think it would do something like that. Would you guys agree with that? Okay. So what I'm going to do, and this one doesn't have any of the numbers or values on it, but you guys can reproduce that on yours fairly well, I think. So as someone said, it's just going to be the other graph, the inverse of the other graph, or just basically flip the other graph. A whole one. And I'm not going to go over any of the descriptions of there because it's all the same as before. The next couple of graphs, though, are going to be really important. There's some regions on these graphs that we need to pay attention to. Can I move on? Okay. These are all in your book, by the way. Okay, the next one. How is this particular graph different than the first one that we had looked at? Can anyone name any features that are different? Say this again. Higher pH to start with, getting closer to the 3 area. Automatically, that tells us this must be a weak acid, if we're assuming the same concentration of acid, the strong versus the weak. What else do you notice?
The slope on how it curves.
Okay, it's got more of a slope. Would you guys agree? It does have more of a slope. Good. We'll talk about why that's true here in a little bit. What else do you notice? The what? The equivalence point is no longer at 7. In fact, it's slightly above 8, isn't it? let's imagine that this was the acetic acid versus sodium hydroxide that we had been doing. Look where it's going to start changing color. Right, actually before it gets to the equivalence point, isn't it? Okay. But you guys all saw what it happened, what it took to get it to change color. It was like a one-drop thing, wasn't it? One drop, change color. Another drop, significantly change color. Okay? Yeah, I know you guys enjoyed that. Anyway, so what you're trying, I'm kind of jumping ahead here a little bit. When you're trying to find a which indicator to use, one, you're already going to have a pretty good idea of what the pKa is going to be. We'll get into that later. Okay. But what you want to try and do is match up the pKa so that it is going to show up in the range of that indicator's range of color change. So as long as you're within that range, you found a good indicator. What else do you guys notice? There's actually one other feature I want to point out. Did you notice the inflection itself is not as large? It's not as long, I guess. Okay. Now, a couple of things I want to point out here. First thing someone pointed out was, the fact that the pH was higher. Weak acid makes a lot of sense. Secondly, this range right here was where it has a sharper increase. The reason for that is, what are we adding to the solution? Base, strong base. We're expecting an increase in pH. But, and I'll just go back to the titration that we did. If we're titrating acetic acid, whoa, got a little crazy there, with sodium hydroxide, what are we getting? Sodium acetate with water, okay? On a net ionic scenario, what we're getting is this. Okay, that would be the net ionic piece of that, leaving the sodium ions out of there, they're spectator ions, okay? The reason why didn't I break this apart into spectator, or into ionic nature? It's a weak acid. Does it dissociate very much? No. So most of the material that's in the acid is in the molecular form. It's not dissociated, so I kept it that way. Anyway, is there anything here that could influence the pH? The acetate ion, right? So not only is there sodium hydroxide in the water, hydroxide ion in the water, there's also acetate ion in the water. So there's actually two things contributing to the basicity. That's why you get a more steep curve here. Does that make any sense? Okay, there's two pieces of base in there now. One of them obviously more consistent than the other. Now, that brings me up to another point. This whole region here is called the buffering region. Why? What's in the solution? Acetic acid and acetate ion. We have a weak acid with its conjugate base. That's a buffer system. So this region right here, this relatively high slope here, is the buffering region. Now, if you recall, you'll want to label that if you can on your graph. It's called the buffering region. On this graph, I'll show you where. Okay? An entire region there is the buffering region. Now, if you remember, yesterday I said where in a buffer system, when is a buffer system most effective? When you have equal amounts of acid and conjugate base. You guys with me on that? Okay. So on this graph, we'll interpret how to do this on your graph here in a second. On this graph, where would the maximum buffering region be? What volume of sodium hydroxide? assuming equal concentrations of acid and base. We start off with 0.1 molar here, and we're adding 0.1 molar sodium hydroxide. Okay, as I add more hydroxide, what's going to happen to this concentration? It's going to decrease. What's going to happen to this concentration? It's going to increase. At which point, where do you think we're going to have equal concentrations of those things? When we've added half, okay, where that's going to be is the half titration part, it's called the half equivalence point. Okay, so on this graph, let me show you the difference. On this graph, that would be at 25 milliliters of sodium hydroxide. That would be the half equivalence point. That would be the maximum buffering or the maximum buffering region per point. Okay. On your graph, that's going to be at what, 12 and a half or so?
Yeah.
Okay. So I would put a little dot there, call that the half equivalence point, and make sure that you understand that that is the maximum buffering point. Maximum meaning can take equal amounts of acid or base. Okay, once again, we note that the equivalence point is right in the middle of that inflection piece, and it is higher than 7 now. So it's more basic. Why is it more basic? Because not only is there sodium hydroxide in there, but there is acetate ion, which is base also. All right. I'm trying to think if there's anything else I wanted to cover on that particular graph. Boom, boom, boom. Oh, and here's the beauty of this. At the half equivalence, or sorry about that. At the half equivalence point, this is equal to that. Makes sense, right? Okay, and that brings us back to this point. Looking at the Henderson-Hasselbalch. If these two things are equal, that equals 1. Log of 1 is 0, and therefore, at the half equivalence point, pH is equivalent to pKa. Something else you'll want to make a note of there. All right, next graph. You'll also be asked on occasion to compare acids. We already did that today a little bit. And I just want to show you what happens to the relationship between the various weak acids. You should have do you have this graph?
No.
How much time do I have?
7 minutes.
8 minutes.
Okay. These are coming in pairs to you. They're coming in pairs, so don't separate. They're not coming in peaches. Don't separate. Don't separate. They're coming in pairs. There you go. Distribute in pairs. I know, this has never happened before. We're having a new situation. Let's see how you handle it.
Jeffrey, come on.
Just add them to the packet.
Yep. Are we missing anyone? Yes, we are.
I need one.
Who's that? You're supposed to go in and do a PK.
All right, and somebody's got an extra pair.
Yeah,
There you go.
I need staples.
Yeah, I know.
I know.
Can't help it.
just keep sharing. My treasure
Did you just call him Gessler? No, is it?
It don't matter.
No. Now you get a 1 on an AP test.
Here's how we're gonna fix it. Who's got this other stapler? Oh,
Destroy my house.
You ready? You ready? Who's ready? Who's ready? Who's ready? People backing up. Yeah, I don't know. Yeah.
I'm worried.
Who else?
Yeah. Banana.
Is it still blue?
Yeah.
Claire, incoming. All right, here we go. Now, looking at this graph. Obviously, this is a nice graph. I think it summarizes a lot of things. Obviously, we have our strong acid down here, starting around 0.1 or pH of 1. As our Kas decrease, look what happens to the inflection points. So the inflection point for this one would be about here-ish, give or take. The inflection point for this one would be about here-ish, and for this one would be about here-ish, and for this one, well, it's way up here, and you can see where that goes. So you might be asked to evaluate strengths of acid based on the titration curves that they give you. All right? Next. Let me see. Here we go. So now we have a weak base and a strong base titrating a weak acid. Okay, so it's or sorry about that, a strong acid titrating both a weak base and a strong base. They put both graphs on the same one so you can make a comparison. Obviously, this would be the strong base because it's got a pH fairly close to 14. It's got a large inflection point. Where is its equivalence point? You know, there's the inflection, so in the middle of that, which is going to put us about there, which, oh, lo and behold, right there at 7. However, this would be a weak base. Once again, you can see that little curve here. We get a steeper slope here. And a pH for about less than 6. We got a couple more of those to cover tomorrow. I would highly suggest doing 11 through 14. 11 through 14. Have a good weekend. Thanks. Somebody didn't remind me. Thank you.
No. Yep.
Hey, as far as I'm concerned, school days. Now, I still got to show up, but it's just chemistry. Who cares about